Okay, so today, or last time, we started to make a transition from the combinatorial description between moments and cumulants to maybe a more analytic by putting cumulants and moments in power series and then see what this means for the functions. So at the moment this is just on the level of formal power series, but soon we will really go over to an analytic description of this. Okay, but let me first recall and also finish the example from last time. So our concern was to rewrite the relation between a sequence of numbers, which we call moments, and a sequence of numbers which we call cumulants, and which have a very precise combinatorial relation, to rewrite this into formal power series. So we had the moments, we put them into power series in an indeterminate set. So this is 1 plus sum over n from 1 to infinity. And I have here the coefficients, these are my sequence of numbers, mn. And then I have another sequence of numbers, kappas, cumulants, which you also put in the same kind of power series, kappa n set to the n. Good, and then we want, usually we have here moments and cumulants which are related by a very precise combinatorial relation, and we want to see what this relation means for the power series. And the main statement was the fact that the multiplicative moment series, which is given by the mn, that this is the convolution of kappa with the zeta function, that's the relation between moments and cumulants, that this is equivalent to a functional relation between those series, which can be written in the form that if I take the cumulant series and I plug in as argument z times the moment series, that this is just the moment series. Okay, and so this can also be written in different forms. I mean, instead of expressing m in terms of c, we can also express c in terms of m, which is also equivalent, namely m in z divided by c of z, this is equal to c of z. Okay, and that this is not only a compact way of writing things, but can also be useful. We saw an example, namely we looked at the example where we have the moments of a semicircle, the cumulants of the semicircle, and we know the cumulants of the semicircle is very simple, and from this we calculated the moments. The moments are given by the Catalan numbers. So this contains this information. Okay, and then we continue looking on the Poisson case. Of course we know both sides, so this doesn't give us anything new. It's just checking that really, this information, how this is contained in these equations. Okay, so let us do as a second example. Before we then really do something new, where we get new information, we consider the free Poisson distribution. If parameter lambda equal to 1, because then again we know both the moments and the cumulants. The moments are again just Catalan numbers, and the cumulants are just all equal to 1. But let us start just using the information about the cumulants. Let us see whether this gives us the information about the moments. So let's say free Poisson. We use the information that this means all cumulants are equal to 1. And then let us check what this here means. Of course, the moments and the cumulants are related by this. The cumulants are equal to 1. So this means this cumulant series in Z, we know what this is. So namely c of z. So this is 1 plus, and then we get here the series where all coefficients are equal to 1. So it's 1 plus z plus z squared plus z to the power of n plus and so on. And of course, this is nothing else than a geometric series, which we can also sum to get 1 over 1 times z. So we have a very, this somehow is still combinatoric, so coefficients are all equal to 1. But on the form power series side, we can also rewrite this in this form, and then of course such an equation gives us quite precise kind of functional relation. Good, But so let us see what we get. So plug it in into this form here. So C is now this. So this means this relation, okay, so this was relation 3. This gives us, so I take C, and as argument I take Z times M of Z. So I have here to replace Z by Z times M of Z, so I get 1 divided by 1 minus Z. M of Z, this is equal to M of Z. And so you see, we get a quadratic equation for the moment series, as we expect, because we know what we should get. And of course, it's exactly the equation for the generating function of the cumulant numbers. So maybe what we have here, if I multiply by 1 minus Z times M Z, I have 1 is equal M of Z minus Z times M of Z squared. Or to put it the other way around, that's how we usually write it, 1 plus, and you know, Z times M of Z squared is M of Z. And this is exactly the equation for the generating series of the cumulant numbers. Okay, so this is for M of Z. M of Z was the generating sequence for the cumulant numbers. Good. And so this means again, the moments of a free Poisson, where all the cumulants are equal to 1, are given by the cumulant numbers. This is also encoded here. But now maybe let us also do an example where we get some new information. Of course, this here is just checking that things fitting together as they have to. But now maybe let us see whether we can get something about the Möbius function. I mean, we know the lattice of the coset of non-crossing partitions has a Möbius function, but I mean we don't really know anything concrete about this Möbius function. But of course, the Möbius function, I mean, also is essentially the solution of an equation of this type. So maybe we should also be able to use this for getting at least some values of the Möbius function. Okay. And of course, the Möbius function is defined if I convolve it with the zeta function, I get the delta function. And of course, this is so. I mean, there is a convolution with the zeta function, so we are in this context. Of course, the Möbius function and the zeta functions, they are functions of 2 variables. Here we are dealing with functions of 1 variable, but of course a function of 1 variable is the restriction of a 2 variable function and the first argument is 0. So also this means what we can at least deal here with is the restriction of the Möbius function of mu and of the delta function. So this means mu of I. If I write it just as 1 argument, this is just mu of 0 pi, and the same for delta. Delta of pi is delta of 0 pi. So if pi is an LCN, of course this is the 0, this is 0 n. Okay, and of course the relation between mu and delta is exactly of this form. Namely, if I take the convolution of the Möbius function with the zeta function, I get the delta function. This was the definition of the Möbius function. It's the inverse of the zeta function in this incidence algebra. Good. Okay, and so we have exactly this situation. I convolve a function with the Möbius function, and I get another function. So you see in this setting now, the moments correspond to delta, and the Möbius function correspond to the cumulants. Of course, now the values here don't really have a meaning of cumulants and moments. But it's just this formal relation which we have between them. So this means the moment function, so that is something which we can write down very easily because this is about delta. Delta we know. So this means M of Z, so this is 1 plus, then I take 1 to infinity, and the coefficients are now the delta function from 1n. From 0n, 1 times set to the n. Because the multiplicative functions which we consider in this context are the ones which are determined by the value of the biggest element 1. Good. Okay, but the delta function, I mean, what is the delta function? The delta function, just of 2 arguments, just checks whether the arguments are the same or not. If they are the same, it's 1. If not, then it's 0. And of course, usually, the smallest element and the largest element in NC of n are different. Only in a very special case, where n is equal to 1, then the poset only consists of 1 element, which is at the same time the smallest and the biggest. So this means in this case, this here is 1, otherwise it is 0. So this is 0, unless n is equal to 1. In this case it is 1, so what I have here is just 1 plus 7. Only for n equal to 1. Good. Okay, and of course the C series, this has the coefficients of the kappas, which are not coefficients of the Möbius function. So C of z is the formal power series, and the coefficients are the value of the Möbius function of 0 and 1, except to the n. Which of course we don't know. At the moment we don't know those guys, and now of course we have a relation between this and this sequence, series in this form, and this should allow us to determine those values of the Möbius function. That's of course what we can do. And for this, so you see, I mean before we always knew the C series, and we wanted to calculate the M series, and then we used this form of the relation. Now we know that the M series, and we want to calculate the C series, so it's better to use this equivalent form. So we use this transformation form in our theorem. So this gives, so what should we take? So we should take the M series, and the M series is now just 1 plus z. So we take just 1 plus the argument, and the argument is this guy. So we have 1 plus z divided by C of z, and this just gives us the C of z again. And you see again, we have a quadratic equation for C of z. So of course this means we are not too far away from the equation from the Catalan numbers, so probably the Catalan numbers show up here again. But it's not directly the equation for the Catalan numbers, but we have to do some shifts. Okay, but so first let me multiply with C of z, so that I don't have divisions. So then I have C of z plus z is equal to C of z squared. So it looks somehow like, okay, this is a quadratic equation. And we can bring it to the Catalan form if we write this C of z. Of course, I should play around and see that this is the right thing to do. I write it as 1 plus z times f of minus z. Okay, and we want to see that this f really is that for this f I get the equation for the Catalan numbers. Okay, so this is now just an ansatz, which of course, because I know where I want to go, that's what I do. But okay, so let us see what we get there. So if I plug this in, then I rewrite this equation as an equation for f. So what do I get? So C, this C here, is 1 plus z minus z. Then I'm adding z, and then I get the square of this. So I get, on the other side, I get the z squared times f of minus z squared. I get 2 times this guy, z times minus z, and the square of 1 is 1, plus 1. Good. Okay, so you see the 1 goes away here, here. This term here shows up on the other side, it's a factor of 2. Okay, so this also goes away on this side. Here I'm just doing one of them. And then, so what am I left with? I have, so let's see, I have, okay, I'm you see everything is multiplied. I have multiples of set. In each term I have at least a set, so I can also divide by set. Okay, this gives me here 1. This is set squared plus set. No, set goes away. Minus set. Okay, so is this okay? Okay, now you see, of course, I have m of minus set. So, of course, maybe I have to write it as m of set. So I replace set by minus set, which means I'm getting 1. So I replace here the set by minus set, so I get a minus sign. I bring this down on the other side, and then I have a set, this side plus, and this here is the set squared. On this side, I have the f of set. Okay, this is now really again the equation for the generating function of the Catalan numbers. So this means this f of set has as coefficients the Catalan numbers, and of course this means I can see what the C has as coefficients. So it's a Catalan numbers, but there's a shift and there's also a sign involved. Okay, so this means f is generating series Catalan numbers. And then this tells us C of set from this equation. So what is this? So this is 1 plus set f minus set. And now I write it again as a power series. So this is 1 plus set times. Okay, f is the series which is 1 plus sum n greater equal to 1. And the coefficients are Catalan numbers, and the argument is now minus set to the n. Good. Okay, I mean if you play around a little bit with this, so I want to write it as a power series and set to the n. So this is 1 plus the sum n greater equal 1. I get Cn minus 1 minus 1 n minus 1. I'm set to the n. So you see, I'm multiplying here set with this, so I get here set to the n plus 1, the coefficient is Cn, which means I have to shift here, and there's also minus sign. So just writing it like this, and so you see the coefficients of this power series are now this guy, but this was from where we started, these were the values of the Möbius function. So this tells us what the values of the Möbius function of 0 and 1 are. Namely exactly those shifted and signed Catalan numbers. So maybe we write this down as a corollary, because that's important information about our post set of non-crossing partitions. So you see the Catalan numbers show up everywhere. And they are also somehow encoded in the non-crossing partitions. Corollary of this, so the Möbius function on NC is given by, I'm really given by a bit of exaggeration because it only, we still don't know all the values of the Möbius function. No? Actually, in NC of n, we know now exactly one value, a non-trivial value, from the smallest to the largest element. But we know this for all n's. So mu of 0 1n is minus first Catalan number multiplied with minus 1 and minus 1. So the sequence of these values of the Möbius function is an alternating sign, a sequence of these alternating signs, and the sequence of Catalan numbers are shifted by 1. And of course, we know a bit more because we know, for example, that intervals, let's say from 0 to something, factorize into intervals for other non-crossing lattices. And we know the Möbius function is multiplicative. That's what we used in one of our theorems. So this means this tells us also values of the Möbius functions, let's say, for intervals of the form 0 to something, because it factorizes. But on the other hand, if you want to know the value of the the Möbius function of something to 1, this is not so clear. Only if something is 0. We know 0 to 1, but if you want to go for general pi to 1, this is not so clear, but maybe in the assignments, in the exercises, maybe we will deal a little bit more with this. Okay, so this is really, I mean, if you know this, and knowing a bit more about lattice of non-crossing partition, this contains essentially all information about the Möbius function. All other values essentially can be traced back to this. Good. So, any questions on this? So, yeah. So, this was somehow the start of shifting from combinatorics to a more analytic description. Okay, so I mean, instead of looking at combinatorial relations between moments and cumulants, and we describe freeness in terms of cumulants, we have conceptually nice formulas, but those formulas are given by summing over non-crossing partitions. And if we want to calculate high moments, these are very big sums. And if we, okay, in general, this looks nice, but it's not so clear what it is useful for. It might be useful for proving some theorems which gives relations between various things. But if we really want to calculate something, then I mean these analytic formulas are much more useful. As you already see here in these calculations. Here we really can calculate. From cumulants we can calculate moments. And we want now do this more general, and in particular we want now to address maybe if we have notion of independence, we want to address now one of the most basic questions. So namely, what is the sum of two independent variables? This is in classical probability theory. This of course is related with the notion of convolution of measures. So the sum of independent random variables is given by the convolution of the distribution of each of them. And there's a very powerful machinery for dealing with this. So that's how usually we can calculate things. And we usually take Fourier transform machinery for calculating things. And we want now to address the free analog of this. So the question, so if I have two variables, x and y, let's say, and I know the distribution of x, and I know the distribution of y, and if x and y are free, I mean, then I know that the distribution of x plus y is determined in the distributions of x and the distribution of y, but the question is how. On a combinatorial level, I mean, we have the machinery which tells us essentially how we should calculate moments of the sum. Okay, but if we really, I mean, for example, we know, let's say one of them has a semicircle distribution, the other has a free Poisson distribution. I mean, we don't know the moment of both of them, but of course, distributions is somehow much more intuitive or better information. Then the question is, what is the distribution of the sum of both? The semicircle plus the free Poisson. How can we calculate this? Now with our formulas, maybe we are able to calculate the moments, but even this is not easy. But do we have a good way of really addressing such questions in general? That's what we want to do. And for this, we really, we're really going over to the analytic side, and then we also interpret this formal power series as analytic functions in the variables. And then we have quite powerful tools from complex analysis at our disposition, which we can use for deriving quite strong and powerful results. And really being able to describe this. But still, so essentially, we want to go over, let's say, from the moments to the distribution. The distribution considered as a probability measure, which means we associate to a sequence of moments a corresponding probability measure. Okay. And in general, this is a bit tricky if the moments have a too big growth. So in general, of course there are probability measures which don't have moments, but it can also be the case that our moments grow too fast, and then the moments won't determine the probability measure uniquely. And in order to avoid such things, At the moment, we restrict to the case of compactly supported probability measures, which means that all those problems have an easy solution. No? So then the moments determine the measure uniquely, and this also corresponds to the fact that essentially we are dealing with bounded operators. No? Okay, then everything is nice. Okay, so essentially we first want to treat this case, and this mainly means that power series which are considered here, which are formal power series, that their power series expansion converges for small or large values of z. Oh, okay, so this means these are really power series expansions of analytic functions. Oh, okay. If I go much further to general probability measures, then maybe I have analytic functions, but I might not have power series expansions like this. Oh, okay, but so now we look first at this situation, and then in the next chapter we will try to go more general. Okay, so what we want to do is the free analog, the classical convolution, so call it a free convolution, and for now we do it of compactly supported probability measures on the free line. Okay, and the technical tool for dealing with this is the R transform. The R transform is more or less the series which corresponds to the cumulants. So what I called before C, some modification of this is called the R transform. Okay, so let me start with the remark, what we want to do. Okay, so first of all, classical convolution. We do the free analog, so maybe that was before, but classical convolution has to do with probability theory. I mean, convolution you can do on many levels of functions, but you can also do it for probability measures, and then it corresponds to probability theory. So classical convolution corresponds to the sum of independent, classically independent random variables. We have so the convolution of two probability measures is the distribution of the sum of two variables which are independent, or each of them has one of the two distributions. Good, okay, so we want to do a free analog of this. This means we want to understand the sum of free random variables. Okay, so free analog, which we call free convolution. So this should correspond to the sum of free random variables. Good. Okay. And of course, I mean up to now, when I talked about the distribution of a random variable, we mainly considered it as a collection of moments. But it's, of course, in some instances, we saw those moments are really the moments of a probability measure on R, but we didn't really look on this in a very systematic way, but now we really want to do this systematic. So if I have self-adjoint random variables in a nice enough frame, then they really should correspond to the moments of a probability measure. And then this means this free convolution should also be an operation on probability measures, not just a collection of moments. Okay, but as I said, the frame should be nice enough, and this means in particular that we are going to restrict at the moment to measures with this compact support. In the classical probability theory, we consider random variables where the support doesn't have to be compact. I mean, for example, the Gauss distribution, the support is all of R. In our context of use, of course, the analog of this is the semicircle, which is compactly supported. Also, in free probability theory, many important distributions have compact support. In classical probability theory, usually most things are unbounded. The analogs in free probability theory are compactly supported, so even if you restrict to this class, we cover a lot of interesting things. Okay, but I mean, we will extend this in the next next chapter to looking on all of them. But for now, just to get started and to avoid problems with, let's say, unbounded operators, and also with the moment problem, that actually, I mean, the correspondence between moments and probability measures is not really one-to-one if you're not restricting to subclasses. We stick, for now, consider compactly supported ones. Okay, good. And I'm saying for this everything works nicely, but we should collect the facts. I mean, all this depends on some facts from measure theory or maybe complex or functional analysis. So let me collect the facts. Huh? Some of them are trivial, some are a bit more complicated. I'm not going to prove them, but I want to make a few remarks. Okay, so let us collect some facts about compactly supported measures and their moments in this context. And first of all, I mean, we should really get an idea what does it mean for the moments that our measure is compactly supported. Because the moments are our crucial ingredient. That's the thing from which we start. Okay. And so if I have a sequence of numbers, when can they be the moments of a compactly supported probability measure? Of course, the sequence of numbers must have some positivity requirement, but this is usually satisfied if we are in a star probability space, because then we have a positivity of our function. Okay, but the compact support of the measure means that the numbers should not grow too fast. Actually, they should at most grow exponentially. Okay, so this is one of the facts, the first one. So let mu probability measure with compact support. And the support of a measure is where I have the whole mass. So outside of this support there's nothing. So this means the probability measure has total mass 1. So this means I find an interval such that the mass of this interval is equal to 1. Which means outside there is no mass. So this means it's M such that my measure is concentrated in the interval, let's say, from minus M to plus M. So just to a final interval. So the mass of this is equal to 1. That's compact support. Good. And then, in this case, I mean, at least we have moments, all moments exist. Then the moments of this guy, which of course are denoted by Mn, is the integral over t to the n t over all of r, but of course effectively I only have to integrate for minus m to plus m. That those guys, they exist, let's say they are finite for all n, so this is clear. Okay, and more interesting for us, they also cannot grow too fast, they are exponentially bounded. Which means exponentially bounded. Actually, the constant of this exponential bound is also this m, this constant m. So this exponential bounded, I mean, at the nth moment, the absolute value cannot grow faster than m to the n. So exponentially n. Okay, the constant here, I mean, exponential bounded means there is a constant such that I have an estimate like this, but in this case, this constant m is actually the m which I have for here. Good. Okay, so this means these numbers are not arbitrary. Now, for example, if you take the Gauss distribution, which you don't have compact support, they grow faster than exponentially. Okay, but the semicircle, of course, they grow like 2 to the n. Good. Okay, and then also maybe important for us for the moment problem that actually those moments determine the measure uniquely. Because usually, I mean, we are not starting from a probability measure and then we look at the moments, but usually it's the other way around. We have a sequence of numbers and we want to see that they are the moments of something. Okay, first of all, there should be something of which they are the moments, but in general, there's a uniqueness problem. So in general, I mean, there are probability measures which are different, but which could have the same moments. But this cannot happen if the measures have compact support. So in this case here, we really are in a situation where the moments determine the measurement. We determine the probability measure mu uniquely. So this means if we find any probability measure, assume that this mu also has the moments mn such that to the n t over r is equal to the moments of mu, then actually this mu has no chance but being equal to mu. I cannot find another one. So then this mu must be equal to mu. And here actually I don't require that mu. I don't require a priori that mu is compactly supported. I mean, the fact that the moments correspond to a compactly supported measure means that I cannot find any other measure, even not one which has unbounded support, which has the same moments. Now, okay, so that's somehow one direction. Namely, if we have a measure, then with compact support, then the moments are very nice. Okay, but for us usually it's the other way around. So namely we are starting with random variables in our abstract algebraic frame. We have moments and then we have to think about can we get from there to measure. Okay, so the second part of this. So if we are now in our algebraic setting and usually okay, I mean, we need some positivity. So it's not just that we want any random variable in just an algebra, but we want a star algebra. And in the star algebra, our state is positive. That's a positivity which we need. So if we are in such a setting, so if phi, so if this is a star probability space, which means A is a star algebra and phi is a state, which means phi is not just unitary and linear, but it also maps A star A to something positive, right? It has some positivity property. Okay, so if I have this, and then if I consider a self-adjoint element, a self-adjoint random variable, which means an x for which x is equal to x star, so A. So if this is self-adjoint random variable, then actually the moments of this guy so if I'm in such a setting, then I can look at the moments of this, but of course the question is, could this be a moment or probability measure, and we want a compactly supported probability measure, but for those we know the moments cannot grow so fast. So we also have to put this as an assumption here. If I'm just in the star probability space and I take the moments as a self-adjoint random variable, then in general I have problems. Then it might, I mean, in most general case, it's not even clear, not even true, that there is a probability measure which corresponds to this. But I need some more structure, and for a compact supported case, this is somehow easy. It's just a boundedness condition of the growth of the sequence of measures. So I assume I'm looking on the self-adjoint X, but such that the moments are exponentially bounded, such that these moments are exponentially bounded, which means that there exists 0 such that phi of x to the n does not grow faster than n to the n. I mean, that's what we need if I want a corresponding probability measure. Okay, and if this is the case, then actually it is true that there exists a probability measure which has exactly these moments. And this is uniquely determined more or less by what we already had in mind. So then the statement is there exists uniquely determined probability measure mu x in R such that phi of xn is really given by the next moment is negative mu x. Okay, I mean this is maybe this is the non-trivial part of all the facts which I'm writing down. In particular, because I just want to start with a star probability space. If I would take a C star or von Neumann algebra space where I have much more structure, then this would follow much more directly. But I mean, at the moment, I don't want to talk about C star algebras or things like this. So I really want to talk about a star probability space. Now, the star gives me the positivity, and if I have, in addition, this boundedness, then I am essentially in a C star probability space. I have bounded operators around. But of course, this is part of proving this. So I'm not going to prove this, but I will make a few remarks. I mean, how one gets this. But this is really the non-trivial. Okay, maybe I have another third part, which maybe also goes from a probability measure to the star probability space. So I mean, all our random variables should be elements in the star probability space. So if I now start from a measure, then of course I should find a random variable somewhere which has this measure as its distribution. But of course this is again quite trivial. I'm just doing this, I could take the infinity space or the continuous functions, but I can also just, in the star probability space, I can just take a formal star algebra of polynomials and defining a state there by using the moments. So I can do this here. But this is again kind of trivial. I'm starting from a compactly supported probability measure for any compactly supported probability measure on R. I'm claiming that I can realize this measure as a distribution of a self-adjoint variable in the star probability space. There exists the star probability space A and phi, and x star, so self-adjoint random variable, such that the distribution of this x, as we just saw, exists in part 2, that this is exactly the root from which I started. Okay, I mean this is more or less clear, so that we also put it essentially as part of the collection of facts here. So indeed, we can take, as our algebra, I take just the polynomials in the formal variable x, let's say. So A are just the polynomials in x. So these are just polynomials with constant coefficients, polynomials in a variable indeterminate x. So this is an algebra, but of course I can also put a star on this just by declaring that x is a joint and then extending it to sums and to products in the way that a star has to be extended. And of course this is a commutative algebra also. So A is a star algebra. I declare that x is a joint. Okay, and then of course I need my state on it, and the state, of course, on x to the n, this should be just the moment of my probability measure, and then I just extend it by linearity. I mean, elements here are just polynomials, and if I know what phi is on monomials, I know what it has to be on polynomials. So this means I define it. Maybe let's say rewrite it for a polynomial. So elements here. So this is a polynomial of x, let's say, and then I'm just integrating with respect to my measure the polynomial in the variable t. So in particular, this means, of course, that the nth moment of this measure is just phi of x to the n, which means the moment of x in this setting is just the moment here, just by definition. Okay, and then of course one has the main thing to check is the positivity of phi. In the star probability space, the phi has to be positive, which means that phi of p times p star has to be positive. But of course this is the integral over p times p star, so this is the integral over a positive function. And of course, this is a measure, which means such integrals are positive. So the positivity property of a measure gives me here the positivity of the phi. Positivity of mu gives positivity of phi. Good. Okay, so this is clearly. The problem is of course going the other way around, which is 2. I mean, a measure has much more structure than just a state on a star algebra, because a measure also has some continuity properties, and they must come out somehow from these boundaries. Good, okay, so let me make a few remarks on this, in particular on part 2. Okay, so let's of course part 1 is trivial. If you have a completely supported measure, then of course the moments exist because I can just bound them by n to the n. And this also gives the bound for how the measures increase. I can use t here because I'm just integrating from minus m to plus m. I can estimate t against m, and then I get just n to the n out of the integral. Okay, let me continue there. So for 1, I mean 1 is the first 2 points are trivial. Which tells me that on a compact interval I can approximate in the uniform norm continuous functions by polynomials. And of course, I mean, a probability measure is, by the Rees representation theorem, the same as being able as a continuous linear functional on continuous functions. So I mean, in order to know an integral, I should be able to integrate over continuous functions. So, okay, and I mean, if I have the moments, I'm able to integrate over monomials, and thus this means also over polynomials. And if I want to go over to a measure, I have to see that this allows me also to get from the knowledge of the integral over polynomials, the integral over continuous functions. But if I'm on a compact interval, I can approximate my continuous function by polynomials in a uniform norm, and under this the integral is continuous. So this means the value of the integral on polynomials determines uniquely the value for those functions. Of course, if I go to all of R, this is not true anymore, then I cannot approximate continuous functions by polynomials. But if I'm on a compact interval, then I mean this really shows why compact intervals are a good situation for the moment problem, because there the moments, the monomials, which means the polynomials, determine continuous functions. Okay, so yeah. Is my Stone-Meyer class, or maybe it is the classical Meyer class setting, just on a compact interval. Polynomials are dense in the continuous functions. Yeah, and then for the uniqueness, I mean, you should also note that actually, if I look at actually, I mean, I'm looking here on a nu, which has those moments, but because the moments have exponential growth, this means the nu must also have compact support. Even if I don't ask the nu in the beginning to have compact support, if I'm asking that it has those moments, which I know that they have exponential growth, because they are the moments of this mu, then I know that also this nu must be compactly supported. So this means I really can argue on a compact support, also for this nu. And then it's normal trust. Here, this context might also be important to know the exponential on moments of nu implies that nu is compactly supported. Good. Okay, but now part 2. So 2 really is a quite non-trivial thing. So there I have a star probability space, and I have a central random variable, of which I assume in addition that the moments are exponentially bounded. And then the question is, where do I get my measure from? Of course, this is a moment problem. I mean, a moment problem is a very classical problem, and I mean, this is part of this. So if I have a sequence of numbers, when can I be sure that those are the moments of the probability measure, and in particular, when do I know that this is uniquely determined? And so what I'm doing here is more or less a way of dealing with the moment problem in general. Okay, so this we have the rough idea to prove of this. And essentially, I mean, what we want to find is an operator on a Hilbert space. I mean, we have to go to analytic setting, and this is usually given by operators on Hilbert spaces. The problem is, for the general moment problem, this might be unbounded operators. And then things are tricky, and this is also the problem with the non-uniqueness. But at least, I mean, that's how we should start. So we should get a Hilbert space from somewhere. And so, I mean, we start, let's say, with the polynomials in a variable y, let's say, which is joint, and then I can define an inner product on the polynomials by using my given moments, the moments of x. So I can define their inner product. I mean, this is more or less the GNS construction, what I'm doing here, for this file. So the inner product can be defined by linear or bilinear extension of, okay, I have to define what is the inner product between y to the n and y to the m, because the rest follows by linearity. And this, I say, should be phi of x to the n plus n. So my operator should be Salvatore. I can bring this on the other side. In principle, I mean, I can write this as times 1 times 1. This is going to be the same as 1 comma y to the n plus m times 1. And this should be the n plus m's moment. But I just define it like this. I mean, the x is the guy which I know. I know the moments of x. From those I start. And because I assume that I'm in the star probability space, this here has some positivity properties, and that's exactly the positivity which I need for an inner product. I mean, inner product has to be positive. Good. Okay, so this means I get here a pre-Hilbert space. So I mean, this is not yet Hilbert space, just these polynomials, because I mean, first of all, I might have a kernel, so there might be elements. The inner product is themselves at 0, so I'm dividing those out, and then I take the completion. So I mean, of course, this is not complete. So I do just the ordinary GNS construction, which one does in operator algebra setting. So I'm dividing out the kernel, and I take the completion. And this gives me then a Hilbert space. Division by the kernel. Completion gives me a Hilbert space. So essentially this is the completion of polynomials in Y. With respect to the norm coming from this inner product. And then of course I have now my operator is now the operator Y. In this space, on this Hilbert space, I want to look on operators on this Hilbert space, and I can do multiplication by Y. This Hilbert space, I mean the Hilbert space are essentially functions, polynomials in Y, and of course I can multiply this with Y to get a new one. So I get a mapping from polynomials to polynomials, and this goes over to a mapping from the Hilbert space to the Hilbert space. Okay, so this means I have an operator. So I take Y, and this acts as a multiplication operator. On this Hilbert space, but the problem is this operator is in general unbounded. If this would be bounded, then I would have a very nice situation and I would have a measure directly. But in general, this is an unbounded operator. In general, it's unbounded, but at least it's a symmetric operator, and one can check that it has a self-adjoint extension. Of course, now one has to use some knowledge and properties of unbounded operators. Okay, so if you don't know about this, forget it. But if you have seen this before, as you should have seen in functional analysis, then maybe at least you can get some idea what this is about. So it is an unbounded symmetric operator, and it has a self-adjoint extension. Of course, an unbounded operator. With self-adjoint extension, maybe I call this Y twiddle. And of course we have that the moments of this Y twiddle are the same as the moments of the Y, because it's an extension. So this means if I take one, Y twiddle and Y, 1, so you are taking this state here on this Y twiddle, this is the same as corresponding quantity in Y, because I mean, the 1 is in the domain of Y, of course the polynomials are in the domain, this Y twiddle is just an extension, it gets a bigger domain, and those are defined as my original moments of the x to the a. Good. Okay, but now, on this Y twiddle, this is now a guy where I know that I have analysis around. So I can go from moments to measure because I have the spectral theorem by Hilbert space, which is essentially about having a spectral measure. Okay, so for this y twiddle, for this y, this y was not a nice enough operator, but it's just symmetric. But we have to go to a several joint one, and this y twiddle is several joint. So this means this equation here, that this, so I can now extend applying this state to powers of y twiddle to applying it to all bounded functions of my y. This is what the spectral theorem gives me in the end. So this here, this extends this spectral theorem for several joint operators on the Hilbert space, but here for unbounded operators. To spectral measure of measure, let me call it my mu twiddle, spectral measure of y twiddle. This means that actually this is not true only for moments, but I can also take the corresponding state for all the functions. So this means if I have enough analytic setting around, then I can go over from moments to measure, because the continuity properties which I need for this are somehow given by the analytic surrounding which I have. And bounded operators on Hilbert spaces have this setting, but also unbounded operators if they are self-adjoint or normal in general. So that the spectral theorem is essentially doing this for us. So this means I also have one f of y twiddle, one, this is the integral of f of t for this measure mu twiddle. Good. Okay, and up to now I have not used the exponential boundedness of my moments. So this really is somehow how you can attack the moment problem in general if you don't have bounds on the growth. But of course the problem is this extension might not be unique. Okay, and if we now assume that our moments are exponentially bounded, then of course this measure here must have compact support. And then everything is uniquely determined, and my operator y is actually a bounded operator. But from the beginning I don't know this, so I have to go through unbounded operators to get the measure mu, and then I know this measure mu, the moments of this have exponentially bound, and then it must be a compactly supported measure, which also means that the y has tend to be a bounded operator. Okay, but you see, one needs quite a bit of quite non-trivial theory for doing this. Good. Okay, but this is just a rough idea of the proof. So, by the exponential boundedness of the moments of y twiddle, which are the moments of y, and those are the moments of x. And for the moments of x, we made some assumption, the assumption of this exponential boundedness. The moments of y twiddle are the moments of x. Okay, so the moments are exponentially bounded of this mu twiddle, which means mu twiddle has compact support. This means the y twiddle is actually bounded, and this means in particular it's unique. Okay, so that's also the point here. We also want to see that in a unique measure. That's also unique. So the several-joint extension of y twiddle, this is just y itself. If my operator is bounded, then of course it's already several-joint. So any several-joint extension is the operator itself. So this means mu twiddle is actually always the same. I get this mu of x. Good. Okay, so this is just the idea. So if you know spectral theorem and all those things, I mean, you should be able to, then it was more or less the proof, or you should be able to fill in the details. If not, then maybe this suggests that maybe it's a good idea to learn a little bit about operators on Hilbert spaces and their spectral theory. Good. Okay, so let me also make maybe one remark to part 3, which is not 1, but part 3 was that I can realize a measure as a distribution of something in a star probability space, and of course the star probability space can also have some more analytic structure. So we can also take a C-star algebra or from Neumann algebra, which usually is the case. I mean, up to now I want to avoid this. So we can also take star algebra A with more analytic structure. So namely we could take for A, for example, a continuous function on the support of mu, which means that it could be a C-star algebra, or we can take the infinity functions with respect with respect to mu, then it could be for Neumann algebra. Of course, commutative ones. Good. Okay. But I mean, I'm avoiding this for the moment because what we need in the next step, I mean, if I want to look on x plus y, if x and y are free, then of course, I mean, I can realize x somewhere, and if I like, I can realize it on a C-star of Neumann algebra, I can realize y there, but then I should take a free product construction, which means I can both realize somewhere. And I mean, we haven't looked in class of free products, but we have to do it on assignments, but there we restrict to the free product on star probability spaces. So this means that this construction, even if I start from two C-star algebras and I'm taking the free product, it's not clear when I get a C-star algebra. I just get a star algebra. So this means with these things I want to stay within formulating things in the star algebra level. If we would also have the C-star free product, which of course can also be done, then one could avoid those things and maybe just realize things directly in the C-star level and also doing the free product there. But I wanted to avoid this here because I didn't want to go into C-star algebras for now. Okay. Good. Yeah, so this means if I have, so we are looking now on operators or random variables of which we assume that the moments are exponentially bounded. Of course, for example, they are moments of a compactly supported probability measure. And we want to look on the sum of such things to get the free convolution, the sum of free versions of this. But if we do the free convolution, or if we are dealing with freeness, then we have seen we should go from moments to cumulants, and then maybe also going back from cumulants to moments. And on the level of the moments, we have seen that we need this compactly supported, this exponential boundedness to having a compactly supported measuring background. Okay, but if you go over to the cumulants, then it would be good to understand what does it mean if the moments are exponentially bounded, what does it mean for the cumulants? Because I mean at some intermediate steps we also have to talk about the cumulants. And we should see that exponentially boundedness is preserved, but at the moment we only know what it means for the moments. And so it's very good that actually being exponentially bounded for the moments is the same as being exponentially bounded for the cumulants. So we should see this, that's the next proposition, because then this means we can go back and forth, and this analytic kind of condition is the same on both sides. We don't need any new considerations for the cumulants. And first we should check this. So, proposition is that, so if we are in a non-commutative probability space, positivity doesn't play a role here, so it's just connecting the growth of moments with the growth of cumulants without any considering at the start. So we can do this in a general non-commutative probability space. And we consider their random variable, element of our algebra. And then we are looking on the moments and the free cumulants of this variable. It's moments and free cumulants by, so the moments, I mean Mn of A, just phi n to the n, clearly. And of course the cumulants, which I denote by kappa n of A, of course are the cumulant functionals where I plug in each argument, I plug in the A. So you are talking about the cumulants of one random variable. I'm taking the free cumulant and each argument is the A. So this is just kappa n. The general cumulant functional in each argument is now A. Okay, and then, so I have two sequences of numbers, and we know they are related by convolution to zeta function. And now I'm claiming exponential boundedness of this sequence of numbers is equivalent to exponential boundedness of this sequence of numbers. So then we follow in equivalent. So first is the sequence of moments. So n of A, the exponential numbers, is exponentially bounded. And the second is that the sequence of cumulants is exponentially bounded. Okay, so those guys are here. Good, so let us prove this. And of course we have to use the relation between them. Maybe let us first go from 2 to 1. This is maybe more direct. So assume we know that the cumulants are exponentially bounded. We want to see that the moments are exponentially bounded. So I assume the cumulants are exponentially bounded. So I assume that kappa n to the kappa n of the variable A is bounded by n to the n, for some n. This is true for n. It exists in n. Good. Okay, and now I have to see what can I say about the moments. Of course, the moments by the moment cumulant formula, or the fact that the moments are the convolution of the cumulants with the zeta function. This is the sum against moment is the sum over all non-crossing partitions of n elements, and then each of those pi's make a contribution which is multiplicative in the blocks. So I get the product over the blocks of pi, and the contribution of each block is a moment, and the moment which is indexed by the number of elements in the block. So it's m of the number of elements in the block. Good. Okay, so now I want to estimate the moment. So this is less or equal, then we have to do the value of this. Good. By our assumption, of course here I have the kappas. So the moments are expressed in terms of the kappas. By my assumption, I know that this guy here can be estimated against m to its index. So this is kappa, the number of elements in the block. And I have a product over such things here for each block. I have an estimate kappa to the number of elements in the block. So what I get here is kappa for the product, is estimated against kappa, and I have to sum over the elements in all the blocks. But the sum of the elements in all the blocks is just n, because the blocks are just a decomposition of my element, my set of n. Okay, here's what I have n. So I'm estimating kappa against m to the number of elements in the block, and then I'm taking the product of all the blocks. And so for this together, I get estimate this and m to the number n, because the sum over all elements over all blocks is just n. Good. So this means I have here sum over pi in NC of n, and each of those pi's gives me a contribution which I can estimate by m to the n. Okay, so I can estimate it by constant term, and so the question is, how many terms do I have here? So this is less or equal. For each of the terms, it's m to the n. And I get how many terms? I get pi's in nc of n. So I get the number of nc of n. Yeah. The elements in nc of n are Catalan numbers, cn. And the Catalan numbers, okay, that's something I should also think about, are exponentially bounded. Namely, they grow at most like 4 to the n. Maybe we got to do this exercise. So this means, I have here the exponentially bound for the kappas, and here I get another exponentially bound coming from the structure of nc of n. So altogether, I have a bound for n to the n. So I have an exponentially bound. Of course, what I have here is not so important, it's just that I find some number. Good, now let's go the other way around. And of course, you see the other way around, I get as an additional complication that I have the Möbius function. So I should also have an exponential bound for the Möbius function to the similar function. This is of course something where I need some information about the Möbius function, and we have seen some basic information about the Möbius function. Again, that they are related to the Catalan numbers in the application of our formula from the last theorem. But of course, one needs more. But this is again shifted to assignment. And then let me do proof. Modulo, what we are going to prove in the assignment. So go from 1 to 2. So I assume now that the moments have an exponential bound. So I assume that the nth moment of A grows at most like m to the n or n. And then I want to see that I have a similar estimate for the kappas. Okay, so the kappas are given in terms of the m's by convolution with the Möbius function. Or it's kappa n a, sum over all cross partitions and elements. I get the multiplicative contributions from the moments, which is again the product over blocks of pi. Each block makes a contribution. M is the index number of blocks in this. But then I also get the Möbius function. I get the Möbius function of pi. That's a general formula. Again, I want to estimate this is less or equal to this times this. Okay, and of course for this we have as before. So this is less than capital M to the number of elements in this block, and if I multiply all blocks together, I get here m to the n. That's okay. Of course, this would give another 4 to the n, but of course, the question is now, what about this? So I need an exponential estimate for this, and again, it turns out that this can be estimated by less than 4 to the n. What we have seen is that I have here a 0 and here 1. Then it's essentially a Catalan number. Okay, and one has to, in general there will be factorizations of this, and it turns out this is a factorization into Catalan numbers, and so I can estimate this by 4 to the n. But we will do this as one of the exercises. So at the moment it might not be so clear. But again, because those guys are related to the Catalan numbers, I hope it's feasible to see that it's also bound by 4 to the n. Okay, so I get get a 4 to the n from here, a 4 to the n from here, and an m to the n from here. So again, I have some exponential bound. Good. And now after all these prerequisites, we can now define what we mean with a free convolution. Okay. A free convolution should be the distribution of the sum of two random variables which are free in terms of the distribution of each of them, and the distribution we want to identify now with a probability measure. So the free convolution should really be an operation on probability measures. And we have now things together to make this rigorous. Let me use the definition, or maybe it's a theorem that this really fits together and it's uniquely determined, if I can put up. So, this is theorem. Good, okay, so we want an operation on probability measures, so we start with two probability measures, but they should be compactly supported. So that mu and mu, two compactly supported probability measures on R. Okay, and then I'm claiming that we can realize this situation by free random variables in some star probability space. So then there exists a star probability space phi and two random variables there, several joint random variables, x star, several joint x, and the several joint y, and yeah, such that the distribution of mu x in this probability space is the given mu, and the distribution of this mu y is the given nu. So we have here a star probability space, and I want a random variable whose moments are the moments of my given mu, and I want a random variable y whose moments in this space are the moments of the given mu. Okay, and furthermore, such that in this space the x and the y are free. Good. Okay, and then we are looking, of course, now on x plus y. We want now the distribution of x plus y, and for this we want, this should be the moments of a probability measure, and the crucial thing is now to see that they are exponentially bounded, because then we know there is a unique probability measure, but this is somehow, this follows, I mean this is part of the statement here, but this is more or less putting together everything before. So the moments of x plus y to the n, so the moments, these are the moments of the several joint die, x plus y, of the self-adjoint random variable x plus y, which of course lives in our A, are then exponentially bounded. Okay, and this means by part 2 of the previous one before theorem, means that they determine uniquely a compactly supported probability measure. So if I have a star probability space and I have a random variable whose moments are exponentially bounded, then they are exactly the moments of a compactly supported probability measure. That's what we saw before. So hence they determine uniquely the compactly supported probability measure, which is denoted by mu of x plus y. Okay, and so this measure only depends on mu and nu and the fact that I have realized x and y in a free way. But But it does not really depend on any other information about x and y. I mean, this here just says I can realize x and y somehow, somewhere in some star probability space, and there might be many possibilities for finding such guys, but the moments of x plus y, of course, only depend on the moments of x and the moments of y, which means it's really something which only depends on mu n. The moment of x plus y, and thus this corresponding probability measure mu of x plus y depend only on mu and on the fact that x and y are free. And the fact x and y are free, but it does not depend on the concrete realization of x and y. Okay, so next time I will say a few words about the proof of this, but the proof of this is just putting together everything which I have said before. I mean, the principle should be clear, so maybe you should think at home about it. But maybe let me finish by giving now a definition. Now, of course, this is now the distribution of x plus y, so this mu x plus y, this is now, of course, what we call the free convolution of mu and b. This probability measure mu of x plus y 4.5 is called the free convolution of mu symbol, so mu, and then I take the plus in the box, mu plus mu. Okay, so this is just a notation for this operation. Classical convolution usually denoted by mu star mu, so this is the notation for the free convolution, and I mean the plus denotes that this is really, I mean, for the additive, you're taking the sum. There's also an analog theory, if you take the product of free variables, then you take times in the box. So we are not going to talk much about this, so we stick with this. So this is now really an operation on the level of compactly supported probability measures on R. Okay, if we have, based on this theorem, which is easy to prove given the things which we did before. Okay, and of course, the main task will be to understand this operation better, and in particular, to be able to calculate it. So if you really have concrete measure mu and a concrete measure mu, can we calculate this here? Of course, in principle, it means, I mean, in this context, everything is determined by moments. So it means if we know the moments of this and we know the moments of this, we in principle know the moments of x plus y, but this in principle is a bit tricky. We can go over to cumulants, then we know in principle a little bit better, but still, we have a lot of cumulants. If we go back to the moments, it's a combinatorial formula, and it's not so clear whether this really gives us a concrete way of doing anything. And so, for example, I mean, if we take the free convolution of Bernoulli, so this would be delta minus 1 plus delta plus 1, Bernoulli with itself, what is this? For classical convolution, this is trivial. In the free case, it will turn out this is not trivial, and it's absolutely not easy. I mean, you could try to do this on the level of the moment, and you can do it somehow, but I mean, we really want efficient machinery so that we can really do calculations like this. That's maybe what you want to do next time. So, good, so I stop here.